Welcome to the video on the Helmholtz and Gibbs energies. Alright, so let us consider a system that is in thermal equilibrium with its surroundings at a temperature T. When a change in the system occurs and there's a transfer of energy as heat between the system and the surroundings, the Clausius inequality is here, can be rearranged to form this equation. And so we can then examine this inequality for either a constant volume process or a constant pressure process. So first let's look at the constant volume process. In the absence of any non-expansion work, which will, so note that if we're at constant volume, then we can't have any expansion work. So if we don't have any non-expansion work, so no electrical work being done or something else like that, then whatever our constant volume change in heat is equal to our constant volume change in internal energy. And that means that now we can take du, our change in internal energy, and substitute that in for our Q here. And so this equation is important because now it expresses the criterion for a spontaneous change, this criterion, that our change in entropy minus the change in internal energy divided by temperature is greater than 0. It expresses now that we have our criterion for spontaneous change only in terms of the state functions of the system. So now it no longer depends on Q, the heat exchange. It only depends on the state functions, the entropy, the internal energy, and the temperature T. So now it doesn't matter what our path is anymore, because remember, a state function doesn't depend on the path that we take from one point to another, whereas the heat does. That is a path-dependent function. So now we can rearrange that inequality to get the this quantity, temperature times our change in entropy, must be larger than or equal to our change in internal energy. So at either constant internal energy or at constant entropy, then we get these two inequalities. So at constant internal energy and constant volume, then the entropy change must be greater than 0. And at constant entropy and constant volume, then the internal energy change must be less than 0, less than or equal to 0 for a spontaneous process. Right? So that's what we had on the last slide. So the first inequality, this one, the one with entropy in it, is basically the second law. The entropy change of a system at constant internal energy and volume must be positive for spontaneous change. The second inequality, this one, says that if the entropy and the volume are constant, then the internal energy of the system must decrease for a spontaneous change. So what this is saying is that if we're not changing the entropy, if the entropy is constant, and we're not changing the volume, then the internal energy must decrease, by which we mean that energy must be leaving the system as heat, because we're not allowing any work to be done. So energy must be leaving our system as heat that's going into the surroundings. So really, we're increasing the entropy of our surroundings. So if the entropy and volume are constant, then internal energy U must decrease for spontaneous change. So note, be careful, don't interpret this as a tendency of the system towards lower energy, right? Which is tempting to say that, but that's not the case. It really means it's a disguised statement about the entropy of our surroundings. So if the entropy of the system is constant for a spontaneous change, then the entropy of the surroundings must be increasing. And the entropy of our surroundings can only increase if the energy is flowing out of the system as heat. Right? So that's really what this equation is saying there, right? It's really a disguised statement about the entropy of the surroundings, right? Because the entropy of the universe as a whole must be increasing for any spontaneous change, and if the entropy of our system, this S, if that S is constant, then we know that the entropy of the surroundings must be increasing. The only way for that to happen is to have energy leaving our system, going into our surroundings. That will increase the entropy. Right. So that was for the constant volume process. Now let's look at the constant pressure process. So if energy is transferred as heat at constant pressure, and we have no non-expansion work, so now we again still have no work. We don't have any expansion work if we have constant pressure. Sorry, that's not true. We're not allowing any non-expansion work, so now we can say that the heat being transferred at constant pressure, QP or dQp, is equal to some infinitesimally small change in enthalpy. Note that this is not the internal energy, it's enthalpy. And so now we get this inequality. So we have our quantity, temperature times the change in entropy, must be larger than or equal to the change in enthalpy. And so again, at either constant enthalpy or at constant entropy, we can rearrange that to get two different inequalities. So at constant enthalpy, so constant H and constant pressure, the change in entropy must be positive. It must be greater than or equal to 0 for some spontaneous change. And at constant entropy and constant pressure, then the enthalpy change must be less than or equal to 0. So the entropy of the system at constant pressure must increase if its enthalpy is constant. That's what this says. And if the enthalpy is constant, then no energy leaves the system as heat. And so the entropy of the surroundings is constant. That means the entropy of our system has to be increasing for our spontaneous change. On the other hand, the enthalpy must decrease if the entropy of the system is constant. And if the entropy of the system is constant, then the entropy of the surroundings must be increasing. Because again, otherwise we don't have a spontaneous change. So to increase the entropy of the surroundings, energy must leave the system as heat, and so the enthalpy is changing. Rather, the enthalpy is negative. Okay, so now we have two inequalities of this form. Right? We've got either du or dH minus TdS, temperature times the change in entropy, must be less than or equal to 0. So now we're going to introduce two new thermodynamic quantities, and note that all of these symbols here refer to the system, not the surroundings. So the first one is the Helmholtz energy, which we use as A, and we define the Helmholtz energy A as the internal energy minus temperature times entropy. So this is not change in entropy anymore, or change in internal energy. These are state functions. And then we have our Gibbs energy, G, which is defined as, so G is defined as enthalpy minus TS, temperature times entropy. Right, so here we have two new kinds of energy. Right, so we already had two other ones. We had internal energy there, that's one type of energy. Then we had enthalpy, that's another kind of energy. So now we have relationships between our four types of energy, and we're using our this quantity minus TS here to relate Gibbs to enthalpy and the Helmholtz energy to the internal energy. So if the state of the system is changing at constant temperature, so now we're not letting the temperature change, so then we can say that the change in the Helmholtz energy is equal to the change in internal energy minus temperature times our change in entropy. And the same thing, or similar, for the Gibbs energy. So our change in Gibbs energy is equal to the change in enthalpy minus temperature times the change in entropy. So now we can show that for a spontaneous change, our Helmholtz energy at constant temperature and volume must be less than or equal to 0. And the Gibbs energy, or change in Gibbs energy, dG, at constant temperature and pressure must be less than or equal to 0 for a spontaneous process. So these two inequalities are very, very important in chemistry because now they allow us to predict the conditions under which a process is spontaneous, if there are any under which it's spontaneous. So now we've basically wrapped up the entropy and internal energy, or entropy and enthalpy quantities together into one new variable, either the Helmholtz energy or change in Helmholtz energy, or a change in Gibbs energy. So, a change in a system at constant temperature and volume is spontaneous if the Helmholtz energy is less than or equal to 0. That's what we had on the last slide. So in other words, a change under these conditions is spontaneous if it leads to a decrease in the Helmholtz energy. So, at equilibrium, the change for both forward and reverse processes, because they're both they both can happen spontaneously. That means that at equilibrium, the change in Helmholtz energy at constant temperature and volume is equal to 0. So if it's equal to 0, then both processes, both the forward and reverse process, are spontaneous. That means they're both happening at the same time, and that means we have an equilibrium. Right. So we can often interpret these two expressions as here. A negative value of dA is favored by a negative value of du and a positive value of TdS. So if the internal energy is negative and the value of TdS is positive, then our value for dA, our change in Helmholtz energy, will be negative. It's more likely that it's negative. If this is negative and this is positive, then dA has to be negative. On the other hand, if du is positive and TdS is negative, then minus the negative is plus the positive. Now we have a positive plus a positive. So that means that our change in Helmholtz energy must be positive. And that means that it's not going to be spontaneous. Alright, so a negative value of dA is favored by a negative value of du and a positive value of TdS. So this suggests that the tendency of a system is due to its tendency to move towards states of lower internal energy and higher entropy. But the tendency of a system to lower Helmholtz energy A is due only to the increase in total entropy. Why? Well, remember that ds is only the entropy change of the system, and this quantity, negative du over T, is the entropy change for the surroundings, because remember, the du here is a measure of the quantity of heat that's leaving our system. If heat is leaving our system, then that means that the surroundings is gaining that energy, and so that's where the negative is coming from. And if the surroundings are gaining energy, then the entropy of the surroundings is increasing. So, really this means that the total of these two quantities, the change in entropy for the system and the change in entropy for the surroundings, those two values tend towards the maximum. The total entropy of the universe as a whole, the system plus the surroundings, tends towards the maximum. Okay, so that's really what this is saying. All right. So note that the Helmholtz energy is more than just a signifier for a spontaneous change, and the change in the Helmholtz energy is equal to the maximum work accompanying a process at constant temperature. So the maximum amount of work we can get out of some process is equal to the change in Helmholtz energy. So this is why A, the Helmholtz energy, is sometimes referred to as the maximum work function. This is the maximum amount of work we can get out of some process. It's also sometimes called the work function. Note that Arbeit is the German word for work, and that's where this symbol A is coming from, right? From that German word for work. Okay, so when a macroscopic isothermal change takes place, then the maximum amount of work, total amount of work that can be done, is equal to the delta A, the change in Helmholtz energy, where the change in Helmholtz energy is equal to the change in internal energy minus temperature times a macroscopic change in entropy. So if we have a system like this, over here, we have our system in the box, and we have some amount of energy leaving the system as heat, and we have some amount of energy leaving the system as work. And so here, if the entropy of our system is decreasing, and the internal energy of our system is decreasing, because we have some energy leaving as work, as heat. Now if we look at our surroundings, the entropy of the surroundings is increasing because it's absorbing some heat from the system. And we have to have more heat leaving the system than we have entropy because of the entropy loss, right? Because this decrease in entropy here must be offset by an increase in entropy here in the surroundings. And so we've got to have a lot of heat being transferred out of our system into the surroundings to offset this loss of entropy in our system. And so that's what's allowing this work to be done. But note that the work here has to be less than the internal energy change because we're removing some energy as heat. So that's where this expression is coming from. So this expression shows that if the sign of T delta S is negative, right, which we had in this case, right? If delta S is negative, then temperature obviously must always be positive, or zero, I suppose. So if delta S is negative, then T delta S will be negative. And so if T delta S is negative, then the change in the Helmholtz energy is less negative than the internal energy, than rather the change in internal energy. And not all of that change in internal energy is going towards work. Some of it has to be going towards increasing the entropy of the surroundings. That's where that heat was going on the last slide. Okay? So this is the origin of the alternative name, Helmholtz free energy. Because this is the maximum amount of energy that can be available to do some work with a process. The other change in energy, the change in internal energy, has to go out into the surroundings. All right, so we can express this statement in another way. Remember that work is the energy transferred to the surroundings as uniform motion of atoms, right? If we have expansion work being done, then the atoms on the outside of our system, as the system expands against the surroundings, the atoms in the surroundings move away in a uniform manner. They're all moving the same direction, outwards. So, because we have this equation, A equals U minus TS, where there A is the total internal energy of the system, U minus a portion of energy that is stored as random thermal motion, TS. And because energy stored in random thermal motion can't be used to achieve uniform motion in the surroundings, only the part of U, the internal energy, that is not stored that way, that's the quantity U minus TS, only that quantity can be converted into work. So any amount of energy that's stored in random thermal motion of the atoms, that can't be used to do work in the surroundings because that motion is in all directions randomly. We can only have the motion in one direction. Okay, If a change occurs with an increase in entropy of the system, so this is different than the last picture that we had. So here the entropy of our system is increasing. It's positive. The delta S is a positive value. So that's what we have here. We have an increase in entropy of the system. Then the right-hand side is more negative than delta U, because we have this equation here. So if this value is negative, if delta S is negative, if delta S is positive, then we have an increase in entropy of our system. If delta S is positive and T is positive, then this quantity here, T delta S, must be positive, and that means that the right side of the equation is more negative than our change in internal energy is, and that means we have more energy available to do work. So, in this case, the maximum work that can be obtained from the system is greater than delta U. So, whatever our change in internal energy is for our system, delta U, that's less than 0. We can get out more work than our change in internal energy because we have heat flowing into the system. So some of this energy that's flowing in as heat is basically being able to be used to do additional work. Alright, so in this case, the maximum work that can be obtained from the system is larger than our change in internal energy. And remember, this might at first seem to violate the first law, that we can't change the internal energy of the universe. But remember that the system can absorb energy as heat, and so that's what's happening here. Right? Energy is leaving the surroundings and entering the system as heat, and that's where this extra bit of work can be done from, is that we're pulling energy out of the surroundings and putting it into the system. Now we can only do that up until the point where the change in entropy of the surroundings is just as negative as the change in entropy of the system is positive. Once the change in energy of our surroundings becomes a larger negative value than the change in entropy of the system, now the process will no longer be spontaneous. Alright, so now let's turn to the Gibbs energy. So the Gibbs energy, often called the Gibbs free energy, just like the Helmholtz energy was often called the Helmholtz free energy. So the Gibbs energy is more common in chemistry than the Helmholtz energy because in normal laboratory conditions, we're interested in changes occurring at constant pressure. It's really easy for us to control the pressure. We just leave it open to atmosphere. That's really easy. And so generally in chemistry, the Gibbs energy is more useful to us. Right, so this criterion that the change in Gibbs energy at constant temperature and pressure is less than or equal to 0 indicates that at constant temperature and pressure, chemical reactions are spontaneous in the direction of decreasing Gibbs energy. Right? So the more, if a process is negative, has a negative change in Gibbs energy, then that will be a spontaneous process. If the reverse process then has a positive change in Gibbs energy, which it will, if the forward process has a negative change in Gibbs energy, then the reverse process has a positive change, then the reverse process, the one with the positive change, is non-spontaneous. Alright, so if the Gibbs energy G decreases as a reaction proceeds, then the reaction will have a spontaneous tendency to be, the reactants will have a spontaneous tendency to be converted into the products, so the reaction will proceed spontaneously. If G increases as a reaction proceeds, then the products will have a spontaneous tendency to be converted into reactants. In other words, the reverse reaction is spontaneous. For example, in a spontaneous endothermic reaction, enthalpy increases. Therefore, the change in enthalpy is greater than 0. But we know that the Gibbs free energy, the change in Gibbs free energy, delta dg, must be less than 0 because the reaction is spontaneous, right? We said it was a spontaneous endothermic reaction. We know that enthalpy is increasing because it's endothermic. We're absorbing energy from the surroundings as heat, so enthalpy is increasing. But we know that because it's spontaneous, dg must be less than 0. Thus, the entropy of the system increases so much so that this quantity TdS outweighs the increase in enthalpy, right? Because dg must be negative, but we know that dH is positive. That means that this value, TdS, must be some positive value, but we know that TdS is bigger than dH, because we need to be able to subtract a larger positive value here than what we have there in order for dg to be negative. So, a spontaneous endothermic reaction is driven by the increase in entropy of the system, and this entropy change overcomes the reduction of entropy in the surroundings brought about by the inflow of heat into the system. As heat is flowing into the system, the surroundings are decreasing in entropy, but this increase in entropy of our system has to outweigh that. So that means that TdS must be a larger positive value than dH is a positive value. And remember that at constant pressure, we have this equation, where our change in entropy of our surroundings is equal to the change in enthalpy of our system divided by, minus the change in enthalpy of our system divided by temperature. And the analog of the maximum work interpretation of our change in Helmholtz energy, delta A, and the origin of the free energy term for Gibbs energy can also be found. So at constant temperature and pressure, the maximum non-expansion work is given by this. So this is the change, this is the infinitesimal amount of work that can be done, additional work that's non-expansion work, so work above and beyond the expansion work. Maximum non-expansion work that can be done is equal to the change in Gibbs energy. And for some non-infinitesimally small quantity, that means that the total non-expansion, maximum work that can be done is equal to some macroscopic change in Gibbs energy, delta G. So now this is useful for determining the maximum electrical work that can be produced by, say, by fuel cells or by electrochemical cells. Okay, so now let's turn to standard molar Gibbs energies. So standard entropies and enthalpies of reaction can be combined to give us a standard Gibbs energy of reaction, or standard reaction Gibbs energy. So we have standard, that's the naught, reaction Gibbs energy is equal to the standard reaction change in enthalpy, standard reaction enthalpy, minus temperature times the standard reaction change in entropy. So the standard Gibbs energy of reaction is the difference in the standard molar Gibbs energies of the products and the reactants in their standard states at the temperature specified for the reaction. So just like for standard reaction enthalpies, it's convenient to define the standard Gibbs energies of formation, delta F G naught. The standard reaction Gibbs energy for the formation of a compound from its elements in their reference states, so in their elemental states. So standard Gibbs energies of formation of the elements in their reference states, in their elemental states, are 0. So we now have an equation like this. The standard Gibbs energy of reaction is this equation. So this is very similar to the standard entropy change for a reaction, or the standard enthalpy change for a reaction. Right? Similar sort of thing, only now we have G basically in place for H or for S. So just as for the standard enthalpy of formation of ions, the standard Gibbs energy of formation can't be found for a single ion. We need to have a counter ion along with whatever our ion is. So the standard Gibbs energy of formation of the hydrogen ion we've defined as 0, just like we did for entropy, at all temperatures. Now we know that it's not really 0, but we're just arbitrarily assigning it to a value of 0, and then we're then able to measure the standard Gibbs energies of all other ions in reference to hydrogen ion. And that was the Helmholtz and Gibbs energies.